Welcome to this deep dive, where we decode the invisible tech that keeps our modern world running. When you stand next to a massive excavator or a high-speed turbine, you see pure, unbreakable brute force.
Right. It feels totally invincible. But that feeling is really a complete illusion. I mean, we think of steel as just this solid block of unbreakable metal.
Yeah.
But at the microscopic level, heavy machinery is essentially fighting a constant, violent war against tearing itself apart.
And winning that war requires engineering that we can't even see with the naked eye. Today, we're jumping into a highly specialized mechanical engineering deck, EP0087 mechanical vocabulary, to figure out exactly how you manipulate raw steel so it actually survives.
Exactly. And to make a machine survive, you have to start with the baseline shape. Specifically, things like the drive shafts that are transferring all that crazy power.
Right, and I always just assumed manufacturers carve those thick ridged teeth, the splines, straight out of a steel cylinder.
Yeah, a lot of people assume that. But carving or cutting steel actually severs its internal structure. So instead, engineers use a process called roll forming.
Okay, let's unpack this. What exactly is roll forming?
Well, it's a cold forming method. They take cold steel and force it under immense pressure between spinning dies, which basically squeezes the ridges into shape without cutting any metal away.
Oh, so it's the difference between carving a shape out of wood versus, I don't know, molding it out of clay.
That is a perfect analogy, yeah.
Because if I carve wood, I cut right through the natural grain, creating these weak points where it can snap. But if I press clay into a mold, the grain just bends to follow the shape.
Exactly. And the material stays continuous. Engineers call that continuous internal grain the fiber flow lines. By keeping them intact, it gives the shaft incredible torsional strength.
So it can handle massive twisting forces without just shearing off.
Right. But strength alone actually isn't enough when things start spinning at high speeds.
Because even solid steel is going to bend when you put it under tons of pressure.
Precisely. Imagine the gears inside a heavy transmission. Specifically, the planet gears that orbit around a central gear to distribute power. Under load, those teeth aren't just pushing,
They're bending.
they're twisting and deforming. So if they were perfectly flat to begin with, that twisting would make them grind unevenly.
So they preemptively alter the shape to anticipate the bend.
Yes. They use what's called topological modification. It's a microscopic, three-dimensional reshaping of the gear tooth surface.
Wow.
Think of it like designing a shoe sole that looks slightly warped when it's empty, but it flattens out perfectly when the weight of your foot presses down. When the heavy load hits, the gear twists right into perfect alignment.
Virtually eliminating friction. That is brilliant. But that structural bending leads us right into the next massive problem, which is heat and friction. Even perfect gears will melt if they aren't lubricated.
Right, they absolutely need oil.
But getting oil straight down the center of a long, solid steel shaft seems, well, incredibly difficult to do perfectly.
Which is why they rely on gun drilling. It's a method that forces high-pressure coolant directly through the drill bit itself as it cuts deep into the shaft.
Wait, how does just adding high-pressure coolant guarantee the hole is perfectly straight, though?
Because it flushes the metal chips out instantly. If a chip gets trapped in there, the drill bit deflects.
And your tonal veers off course.
Exactly. By continuously blasting the debris away from the cutting edge, the bit stays perfectly centered.
Making a flawless tunnel for oil.
Yeah.
But the outside of the shaft, like where the bearings sit, takes an entirely different kind of beating. Here's where it gets really interesting.
Yeah, the external armor.
Right. Our sources mentioned they use lasers to melt a cobalt-based alloy powder onto just those specific bearing seats. But why bother with targeted laser melting?
What do you mean?
Like, if friction is that bad, why not just build the entire shaft out of that tough cobalt alloy to begin with?
Oh, because a tough alloy is usually very brittle. You need the main body of the shaft to flex and absorb shock.
Which is what the base steel does.
Right, but you need that precise ring where the bearing rubs to be practically diamond hard. So laser cladding fuses that wear-resistant armor exactly where it's needed.
Creating a permanent bond without sacrificing the flexibility of the whole piece. Okay, so we've cold-rolled the steel, bored a perfectly straight oil channel, and armor plated the outside.
Yeah.
But grinding and laser melting generates intense localized heat. How do you know you haven't accidentally damaged the metal structure underneath? You can't exactly crack it open to check.
You don't have to. Manufacturers use Barkhausen noise testing to sweep for microscopic flaws.
Okay, I need an explanation here, because listening to solid steel sounds made up.
I know it sounds crazy, but what's fascinating here is that it all comes down to magnetism. At a microscopic level, steel is full of tiny magnetic zones called domains.
Like thousands of microscopic compass needles clumped together.
Yes. When you apply a magnetic field to the steel, those domains snap into alignment.
So the metal becomes magnetized.
Right. But as they snap into place, they physically interact with the microscopic structure of the metal. If the metal is healthy, they move smoothly. But if there's a hidden grinding burn or a microfracture,
The needles get stuck.
they get stuck and then suddenly jerk past the damage. That jerky movement creates a tiny electromagnetic pulse.
An electromagnetic noise. So what does this all mean? We are literally listening to magnetic noise to diagnose hidden injuries inside solid metal.
Yes. By placing a sensor on the gear and sweeping a magnet over it, we can literally hear if those domains are snagging on invisible damage. It's a mandatory step in quality inspections.
That is just incredible to think about. The next time you rely on a high-speed vehicle or watch heavy machinery, just remember the intense invisible engineering happening underneath.
Right, it's not just big chunks of iron brute forcing their way through the world.
No, it's a symphony of microscopic surface tweaks, laser-melted alloys, and perfectly aligned steel fibers working to keep you safe.
And it really forces you to wonder about the next evolution of all this.
What do you mean?
Well, we're currently sweeping magnets over parts to diagnose hidden injuries on a factory floor. But what happens when we embed those sensors permanently?
Oh, wow. Like a machine with its own built-in magnetic nervous system, constantly feeling those microscopic domain shifts and diagnosing its own invisible injuries before a failure ever occurs.
Exactly.
Now, that definitely changes how you look at brute strength. Something to think about next time you see a crane in action. Thanks for diving into this with us.